Hey, hello everybody. Let me swing around here. I got a question today about number, 67. So I thought I'd make a video solution, and a little different than in the past. I mean, in the past I just had my camera down on my desk, and you can kind of see my hand and my arm working on my sheet of paper. But today I was at school and in the lab and making video labs for the following week, and I go, I think I'm pretty much done for the day. I've got as far as I can go, but maybe I'll just make a video solution using the camera instead of waiting until I get all the way home and then setting up the camera there. And I go, I'll try this, although I still have to take the camera and download it. So I don't know which would be faster, but my first reaction is this would be faster. Certainly would be different. So that's what I'm going to do here. So I've zoomed to the camera kind of in this one board. This will be like one sheet of paper. And so I'll just keep going back and forth and working it out. But let me just kind of mark here. Let's see, look on the camera. So it looks like from here to about here, you guys can see on the camera. So let me just put this for starters, chapter 30, number 67. And 67 can be a bit of a challenge. It's got two pieces really to it. One is the conceptual side, and then the other side is the mathematics of it. Both of them are a bit tricky. Now, I think once you see the conceptual, you'll get the idea. In fact, this is kind of drawing on your knowledge from Physics 121. We did problems like this in terms of the center of mass. But let me just read the problem here. It says that a long cylinder conductor of radius A has two cylinder cavities of diameter A through the entire length as shown in the figure. So they give a little cross section, and it looks like this. Here's the cylinder, if you will. It's got a radius of A. And along this wire, and so if I tried to make it 3 dimensions, it would kind of go back like this. There is a borehole drilled in it that has a diameter of A. Yeah, forgive my drawing, those aren't very good circles there. But again, if the radius here is A, that makes this then diameter of A. And that's what they're saying. And so these are hollow spaces, if you will. So the current would all be flowing through this part. This is the part where there is metal. Let's just say it was a piece of copper that we started with, and then we bored these holes in them. This is where the current density is. And so I'll just say there's a J. There's a current, and they say the current is flowing which way? I'll keep reading. A current of I is directed out of the page and is uniformly throughout the cross-sectional area of the conductor. So there is a current I, it's flowing out of the page, and it's spread out not over a whole circle, but what's left of the circle after we cut these holes in them. Now, if you go back to Physics 121, we did problems a little bit like this. We did something like this. We had, okay, let's say you had a cylinder, and you might ask, for my cylinder, where's the center of mass? Now, this is a pretty easy one. It's right in the center. But what if you were to cut a hole in it? And then how do you handle something like that? And here was the magical trick. The magical trick was to say, think of this as two objects, one that is solid and another one that has negative mass. Because when you put an object of negative mass, which of course doesn't really exist, but mathematically we can just put a minus sign in front. So with negative mass, where there is positive mass, the end result is empty space, zero mass. And it's fairly easy to find the center of mass of two objects. Well, I shouldn't go through the center of mass calculation, but that was kind of the logic. And so finding the center of mass when you had two solid objects we did first. Then finding the center of mass when you drilled a hole was actually pretty easy because you just thought of that as a solid object and another object that had negative mass. So when the two were put together, you had an empty space, a hole. So here's what I'm going to do. I'm going to take that idea and extend it into my magnetism now. Here's what I'm going to do. I'm going to treat this right here as, so let me kind of erase this, as three wires. I will have a solid wire that is flowing towards you and has a radius of A. And then I'll have two more wires that have a diameter of A with the current flowing the other direction. So this would be flowing out with some current. This would be flowing back with some current. And you see that if you put this one inside of this one, and they have the same current density, this one that is flowing forward and then this one that's flowing back ends up with no current. And that's exactly what we have here. We have no current. So my approach for this problem is not try to do some kind of integral to figure out what is the magnetic field from a crazy shape like this, but to know that I can think of that shape as being made out of three wires. Now, let me just erase this for a second. So I'm going to ask this question: what is the magnetic field from a solid one? What is the magnetic field from another solid one with current going in the other direction? And what is the magnetic field from another solid one going in the other direction? And then I lay these inside of those and then just add up the field. All right. So to give me a little space to work, if you'll let me go ahead now and erase this, now that I hopefully got the conceptual strategy across here, then maybe going in green, the problem goes on to say, find the magnitude and the direction of the magnetic field in terms of mu naught I, R, and A at the point 1. And then for question B, at the point 2. So point 1 is right here, a distance of R away. And using this strategy, thinking of then this as a solid wire and these as two wires, let's talk about the big solid wire. If I take my right hand, so right hand rule number 2, and I hold it in the thumbs up, and I point my finger in the direction the current is flowing, and I look at my fingers make big circles around it, and so I will then say that this is creating a magnetic field. Why don't I just call it magnetic field number 1? And so the big one would be creating a field that way. And it's just a long straight wire. And so I'll put that equation on the board here. But that's, I think, probably the easiest part of the problem, is what is the magnetic field from a long straight wire. And so we just have 3 long straight wires. So let me do the other 2. The top small one with the current going in would be grabbing my right hand and looking at the field, and so it would be pointing in this direction. Let me call that one number 2. And then this one, again with the current going in, would loop around, and let me call that one number 3. And let me make the arrowhead a little bit smaller, because this one here is further away than this second one. So the strength of the field, even though they're in the same direction, is going to be a little weaker for wire 3 compared to wire 2. So I'll say it again. Conceptually, I'm just going to add up 3 fields. All right. So let's start this way. So answering A, what is the magnetic field at point P1? I guess I would say magnetic field number 1 has a magnitude of mu naught times the current from number 1 divided by 2 pi r. Now, here's where we probably want to be a little careful. In fact, we want to be very careful here. Because my I here and the I that they have are not the same. Why? Well, did you notice that I am saying that I have to have the same current density? And I realize that their current I is spread out over this. It is not spread out over a whole uniform one. So let me just draw a big wire and two little wires again. Because if I look at the area of this, the area is pi times the radius squared, which is A. And if I look at the area of these two little ones, which is pi times their radius squared, so that would be A over 2 squared, and so that would be pi A squared over 4 for each of them. So the total of the small ones would be a pi A squared over 2. Now, what I'm trying to illustrate here is they gave me really some nice fractions, I guess, evenly distributed in 4 parts. In other words, if you look at one of the wires has 1/4 of the entire area. So if we call this the entire area, right here, then 1/4 of that area is this hole right here. Another 1/4 is this one. That means this side, that's solid, that has current, is another 1/4, and this side over here is the other 1/4. And so this weird looking shape actually has the same area as this hole. Okay? So this is divided into 4 equal areas. Now here's what I'm getting at. If we say that the total current is actually I, and it's spread out over these two, if you were to think of this as being solid, then these two would have that same amount of current as here. And so this right here, thinking of it as a solid piece, would have twice the current as what they're calling I. Okay? So again, ultimately, I want to make sure that I have a current where the total I is in this 2 areas. And that to do that, I need to think of this as being solid, and actually solid and carrying twice as much current. So that when I use the small ones and make the current go back and they cancel off, I'm left with I coming this way. So current number 1 needs to be twice what they call I, and so don't confuse what they are calling in the problem I, okay, and then what I'm calling the I being the current in a solid piece. So I'll say it again, to get the same current density, I would have to have a solid piece that has twice the current. And then eventually we're going to cancel off half of it, so the result is just a current of I. Let's do the same thing then with the magnetic field number 2, which again would be U times the current in number 2 over 2 pi, and I'll call it R number 2. And so I'm going to go to this current I. Now in this case, I want to get the same current distribution, and so how much current needs to go back? Well, as I was saying, and I hope this is making sense, that I would want a current going back that would have the same density. And the two of them together should be a current of total I going back. because again I want that to be an I going back and canceling off one of the I's and still leaving I coming forward. You know, or put another way here, right? If this is I coming forward, half of I is in this area, half of I is in this area, and so these need to be half of I going back and half an I going back. So this is going to be a current of I over 2. And the distance away is measured from the center. And the center of this wire is not at the origin. So in terms of R, this would be R, I mean, we need this distance. And so it would be R minus an A over 2. So this is an R minus an A over 2. And if you'll let me, by the extension of that, field number 3 would be the same thing. It's going to be this wire number 3 with the current going back that way. And again, the magnitude of current number 3. So maybe I'll just write it as current number 3 and then 2 pi r times the distance of number 3. But number 3 would be I divided by 2 to write it in terms of the value of I, because that's what the problem says. Write the answer in terms of the value of I. So that's kind of the tricky part about making these negative currents, if you will, is that you got to figure out, well, how much is the current got to be equal to in order to cancel off. And so I'll say it again. For the total current to be I, this area here would be I over 2, and this would be I over 2. So the total current in a solid one coming this way would be 2I, so that this could be an I over 2 and an I over 2 going back to cancel off, leaving with just a total of an I. So each of these little ones must have a current of I over 2. And the distance away is a little bit further. This one down here would be this distance R and then plus an A over 2. So it's R plus an A over 2. It's further away. That's why I said earlier when I was drawing the magnetic field and I was putting that in green, I was saying number 2 is going to be bigger than number 3. And you can see that here because this is R minus a little bit and this is R plus a little bit. And they're in the denominator there. Okay, well, maybe I don't have too much board space to work with. So maybe to complete part A, I'll clear this part off and say, okay, now let's go ahead and get the total field. So the total field, and I'll call the left positive, that's kind of the reverse of tradition, but it's going to be a little stronger field, I think, that way. So this number, I'll call the positive. So this is the mu naught, the 2I over 2 pi r. That's the positive one. Then I will have a minus over here. And maybe I should have simplified this a little bit. But this is going to be then the mu naught, the I, and that's going to be over a 4 pi. And then this would be an R minus an A over 2. And then minus this one down here, which would be a mu naught, an I, and then that 2 and that 2 is going to make a 4 pi. And then this is an R plus A over 2. Okay, now looks like we've still got quite a bit of work to do because now we have to put 3 fractions together. And maybe I'll start with factoring out the common factors, and that would be a mu naught and an I, so each of those are in there. Maybe I'll also factor out a pi, and I guess that would leave a 1 over r here. That would leave a 1 over 4 r minus a over 2. And another minus 1 over, and I factored out a pi, so that's a 4, and that's an r plus an a over 2. Now, of course, now I need to get a common denominator. And, well, an easy way to get a common denominator is multiply all the denominators together. That's not always the lowest common denominator. In fact, I can see that if I do this 4 times that 4, it's 16. So it looks like a lowest common denominator would be not to multiply the 4 up, but to include a 4, include an r minus a over 2, and also include an r plus an a over 2. So to get this one to be the same thing, it looks like I had to multiply by not only a 4, but also an r minus a over 2 and an r plus an a over 2. And then this one already has the 4 and the r minus the a. So it has that and that. So we would have to multiply by an r and then an r plus an a over 2. And this one here already has a 4 and an r plus an a, so it would have to be an r and then an r minus a over 2. And so that would be our mathematics. And it looks like I've still got quite a bit more to do here. Maybe I'll continue on with saying, okay, I've got a mu naught, I've got an I, and maybe I'll just do the denominator, because this is a nice set of mathematics. Maybe you remember, this looks like an a plus b times an a minus a b. So if I leave the 4, the pi, and the r alone, so there's the 4, the pi, and the r, then this right here would be a squared minus a b squared. So that would be an a squared minus a over 2 squared, right? A plus b times a minus b is a squared minus b squared. Okay, so that's what that one would simplify to. Across the top, I still got the 4. But again, notice right here I've got that same thing. I've got a plus b over an a minus b. So there's the difference of our binomial, our plus and our minus. So this would be the same thing. This would be an r squared minus an a over 2 quantity squared. This one here would then be a minus an r squared and then minus an AR over a 2. The next one here would be another minus r squared, and then this becomes a plus, and it looks like another a and r over 2. And so I don't get myself confused, let me put that in here. Oh, and that might have gone off the video here. Where's my hand here? Right. I guess I can't tell this far away here. So let me make another line here that will make it a little shorter. And so here is the mu naught, the I, the 4 pi r. And I'll leave downstairs alone. This is r squared minus, well, I'll do it the a squared over 4, why not? And then up here, this first one is really a 4r squared. And when you take it with this r squared and this r squared, you're left with 2r squared. So there's the r's. And that would be that one and that one. And then these two are equal and opposite, so they just cancel off. Okay, good. And then this right here would be a minus. And when you square that, you get an a squared over 4. And then so times that is just the a squared. Okay. So then I've got a mu squared, I've got an I, I've got a 2r squared minus an a squared. And maybe I'll take this 4. So I'll go pi r. And this would be then a 4r squared minus an a squared. And that's the difference between 2 squared, so we could factor that. We could also factor that one. But I don't see an advantage of that. In fact, I'm going to use this as an opportunity to say, okay, what did they get for the solution? And so they've got the mu naught, the I, okay, good. They've got the, where'd it go? They got the pi over r, okay, good. Pi over r. Then in the numerator, they got a 2r squared minus an a squared, good. And then the bottom, they got a 4r squared minus an a squared, yay! And then they say to the left. And so I've called this positive if it's to the left. And it would be because, see, this is why r squared is always going to be greater than a squared once we're, in this configuration. Now, inside's a little different, but outside, r squared is always bigger than a squared. And so that's a positive number, and that's a positive number. And anyways, it's positive. So the field's going to go that way. And that's going to be the answer. Okay, now, with that in mind, let's play the same game for part B. Part B, then, and to make life a little different, why don't I clear off the board here of all this algebra. Do part B, which I think is a little bit harder because of the angles involved. And so maybe in blue here, I'll make a distance of r out to here and go, okay, there is 0.2. But let's do the same thinking. That there would be equation for B1, and there would be an equation for B2. Let me hold off on B3 for just a second. But as we said, for number 1, thinking of this as solid, the current in the solid one coming out would be twice I, so there's I, and then it would be over 2 pi r. So this is still the same. Of course, now we're calling this distance the r, so we're going along the x-axis. Maybe I better go back to the picture here, make sure I'm looking at it correctly. Yeah, so this is the r. Now, the magnetic field, though, for number 2, so calling this one number 2, remember, was this mu naught times current number 2 over 2 pi, and I'll call it r number 2. But as we argued, current number 2 would have a value, and it would be going into the board. So we'll talk about direction here in a moment, but it would be going into the board, and it has this number. And then it's over 2 pi, and R2 then would be this distance. How far are we from the center of that wire? And to do that, we need to do Pythagorean's theorem, because across the x-axis is r, and then coming up is a over 2. So this would be the square root of r squared plus a over 2 squared. And so that would be the magnitude of B2. Now again, I'll talk about direction, but I wanted to just point out here that then number 3 is exactly the same magnitude, right? It's to the center of number 3. And number 3 is down a little bit. So unlike part A, where I said the field from wire 2 and wire 3 were different because they were different distances, now I have to say the field is the same size. Now, it doesn't necessarily mean it's the same direction. So let me go to our standard green marker here and talk about direction. All right, so let's look at wire number 1 and wire 2 and wire 3. So wire number 1, if it's coming out, I can do this right-hand rule. My thumb in the direction of the current, the field would arc around, and so right here, going straight up, is what I would call the direction of number 1. Whereas number 2, my thumb is going to go in, it's going to curve around, and it's going to be tangential to a circle that is centered at here. So it's not straight down, it's angled inward a little bit. It's, you know, there's a 90 degree between this line coming out and the green one. And that's an important step there. And you see the same thing with number 3. Number 3, if I take my right hand here and I point my thumb in and I curve it around, and maybe for a better picture, I don't know, let me do the vertical line here. But again, number 3 would not be straight down. Number 3 is kind of below. It would be perpendicular to this line coming out, and so it would be angled off like that. Now, here's some good news then. If this is some angle theta, because this is above the center line, then this is below the center line, and so this angle is actually the same. And I'll use that to my advantage here, because if I then want to write, well, what is the total magnetic field, I can see that the left and right, what I'd call the x-axis, of number 2 and number 3 cancel off, and I just have the vertical components adding up. So I would say this is upward because of B1, and then minus the, and I'll say the y component of number 1, but doubled. That's probably worth repeating our vectors here. These two are angled down, so there's no x components. There's only going to be a y component. So when I write the total magnetic field, the x component is going to be 0. But the total field then is going to be in the y direction. And number 1 is pure up, all up. And then I have to subtract the y component of number 1 and the y component of number 2. But I'm trying to argue that the y component of number 2 and number 3 are the same. So I'm just going to double the y component of number 1. Because I already showed they have the same magnitude, and now I'm trying to show you they have the same angle. So they're going to end up having the same y component. Okay, so that way I won't even have to worry about number 3 at all here. Oh, I'm sorry. This should be number 2. Number 2, y component of number 2. And I don't have to worry about number 3 at all. Okay. Now, one more thing before I leave the picture, because I got a lot going on in this picture here, so maybe a different color would make it stand out. But remember, if this is magnetic field number 2, then this is 90 degrees. This radius going back to where number 2 is, and the field is 90 degrees. But also remember, another 90 degrees is between this horizontal line coming out to number 2 and a vertical line. Now here's why that is important here. Because these two 90 degrees share that angle. So if I have called this angle theta, then this one right here must be 90 minus theta. But now remember, this angle plus this empty one has to add up to 90, so that means that angle must be theta. So I got the y component by looking at this, but of course I need the cosine of that, and I'm probably better to look at that angle to get the cosine of it. You'll see that here in just a second here. All right, so let me keep going through the mathematics here. Where's my black one? Okay. So the field from number 1 is this, and so I'll just cancel off the 2's and get a pi over r for the magnetic field for number 1. And then minus 2 times, and this I'm going to write as the magnitude of number 2 times cosine of the angle. And so coming back to here, that's how I get the y component. I'm looking at the cosine theta and I want the adjacent piece. So that's cosine of theta. Okay. Now let me not go too far off screen, but I think this is going to get kind of long here, or wide. This would be mu naught I, or both. It's going to be a long problem and a wide one here. So there is number 1. Let me just leave that alone. And then here's the 2. Now let me put what we talked about earlier. The magnetic field, the magnitude of number 2 is this one here. So let me write it as mu naught times I over. And then let me put that 2 together with that. So that would be a 4, and that would be a pi, and that would be the square root of r squared plus a over 2 squared. And then I have the cosine of theta. And this is where I'm going to come back to the picture. Of course, I got this cosine of theta by looking at this green theta there. But as I argued that this would be the same as this theta in the orange. And so if I do cosine, it would be the adjacent, which is r, over the hypotenuse. Okay, so the adjacent is the r, and the hypotenuse, well, that's how we got this before. Let's do it again. The hypotenuse would be the r squared and the a over 2 squared, and taking the square root of that. So this is an r squared plus an a over 2 quantity squared. So that right there is the cosine of theta, okay? And then this in here is the magnitude of B2. And for that matter, also the magnitude of B3. That's why we have that factor of 2. All right, so maybe now we should look for any kind of common factors here. And what I see right away is a mu naught an I over a pi. So if I factor out from the first one a mu naught an I and a pi, I'm left with a 1 over r. And then this one here, let's see. If I factor out a mu naught and an I and a pi, okay. And if I maybe take a moment to cancel that to a 2, it looks like across the top I would have just an r. And on the bottom I would have a 2. Now this pi is what I factored out. And then these two are the same thing. So this just becomes an r squared plus an a over 2 squared. Nice. And now I'm left with some mathematics again. I got to combine two fractions. I need a common denominator. Okay, so this is mu naught I over pi. And again, the common denominator would be a 2, an r, and it looks like an r squared plus an a over 2 quantity squared. Okay. So maybe I should have given myself a little space here because I think it's going to take a little bit. All right, so this already had an r, so to get this to the same thing, I would have to go 2 times an r squared plus an a over 2 squared minus. And this fraction already had a 2 and an r squared plus an a squared. It's just missing an r, so multiply by another r would make an r squared. Okay, I guess I didn't need a whole lot of space for that one. But so that I don't go off the screen here, And I think we're almost done once we simplify math. So I'm going to go ahead and take a risk here and erase my picture and even these earlier equations that were saying what's the magnitude of the field, and then put this over here and say, okay, this is the mu naught, this is the I, this is the pi. And maybe for starters, I'll leave the 2r and then the r squared plus the a over 2 squared alone. Let's just take a look at the top here, because here would be a 2r squared. Hang on, I think I needed a parentheses here, didn't I? Let's see, to get it, I already had an r, so I had to multiply by 2, yeah, okay. So this right here would be a 2r squared, but then there's a minus 1r squared. So I would be left with just an r squared there. And then this one would be a plus, and it looks like we would have an a squared, and this would be a squared over 4. But when we multiply by that 2, it becomes a squared over 2. Okay, well, I guess I'll keep going here. I've got a mu naught, an I. Why don't I just group this together as 2 pi r right here. And then this one I'll write as an r squared plus an a squared over 4. Once I multiply that out. Oh, and it's not quite the same thing. Okay, so this is an r squared plus an a squared over 2 up here. And maybe to get things to work out, I will multiply top and bottom by 4 so that this becomes a mu naught I, and this would become then a 4r squared and then a 2a squared. And this down here would be 2 pi r, and then this would be a 4r squared plus an a squared. And I think that's about as simple as it's going to get. It depends what form they want. All right, so they have a mu naught I. Now they don't have a 2 there. They've got the pi r. Oh, I see what they did. So then they put that 2, okay. So they've got a mu naught I and they got pi r. And if I put that 2 into here, that becomes 2r squared plus an a squared. So that kind of, this 2 reduces the numerator a little bit, and I'll still be left with a 4r squared plus an a squared. So is that what they have? There's the mu naught, there's the I, there's the pi, there's the r, there's the 2r squared plus the a squared, and then this is the 4r squared plus a squared. Yay! Okay, so there it is. A lot of algebra, but maybe the most important thing is that conceptual idea. Take what you learned in Physics 121. Of course, we were doing mechanics, and so it was center of mass stuff and moments of inertia stuff. But we can treat a negative mass, and in this case, it's a negative current. That's kind of the big thing. But that's only one big thing, because then we've got to figure out how much current goes in each of those wires and where they're measured from. So we've got to remember what R is equal to. This gives me a chance to say, you know, don't forget to read the math, don't just do the math, and then what direction and cosine of the angle. So really good problem. I can see why it's a magenta problem at the end. All right, so hope that helps.